First, I'll just mention that hopefully next Wednesday, Sophia next Wednesday I have a meeting with this reference group representative. So her mail address is on the homepage, so please, if you want to say anything about any issues about the course, either this or that, or suggestions or whatever, critics, so please come forward. Of course, you can just talk to me as well. Hopefully that's okay. So, any suggestions is fine. Yep. Just take this down, I think. So, we won't bother by it. Okay, before we continue with our so-called singular perturbation analysis, I was asked a question last time about this this kidney modeling. If we have a different perspective here, remember the secondary channels and the main channel. Of course, and we assume that the salt concentration was the same as the tissue concentration in the main channel, but that couldn't be completely true, can it? Because that's where we dispose all the salt. So really, we should see at this more complex system where we have these secondary channels coming in, having a certain, say, density, number of channels per square centimeter of the main channel. And really include all this in the modeling. And then we would have, if this is the, say, set direction, we would have a salt concentration in the main channel that increases when we go downwards. That means that the boundary condition on each of these secondary channels should vary and be given by this one. Then you can maybe speculate. And if this salt, of course, the Cm is a bit higher than C0, so the effect of diffusion is diminished when the salt concentration increases here. However, if the water rate increases in the main channel, probably this will be less because it's more easily transported. So maybe we should have different types of secondary channels depending on how far down you're. Maybe we should produce a lot more water in the start, just kind of speed up the channel speed, and so forth. So you can kind of think more about it, but we have, in a sense, control over each of these, except now we get the coupled system because the boundary conditions for each channel depends on what the other channels have done. So you can work it out. So just a thought after I was asked this question about C0. I don't know if anyone has modeled this, maybe no one has, maybe it's a bad idea, I don't know, but something like that. Okay, enough of that, just to finish this kidney stuff. Okay, so we're doing so-called singular perturbation. Today we'll do that on differential equations. Last time we were looking at, just to give a small recap, at the second degree equation, and where epsilon was a small number, small positive number, and naively, since epsilon equals 1/1,000,000th or whatever, this equation would be like that. So we get this simple solution, but it's only one single solution. So could we somehow find an approximation to the other solution? So one thing we would know then is that is that the first term, epsilon times m squared, has to be counted in somehow. So then our thought was, okay, when epsilon is small and we're close to the other root or solution to the equation, could there be two terms that dominate over the third term? And then we did some kind of experiment on this equation, looking for a consistent way to wonder about how we could approximate the equation by throwing away one term that's not important. So if epsilon m squared and 1 are important, that means that epsilon m squared has to be more or less equal to -1, since the third term is small. But then we see that if I solve this one, we get this imaginary solution. That's okay. But what we see is then is that if we assume that these two are of the same scale, then 2m will go to infinity when epsilon goes to 0. So then 2m cannot be disregarded, of course not. So it couldn't be the first and the last term. So how about this one? So then we will have m equals to this one. M equals 0 is a bounded number, so epsilon times m squared would be 0. So that would be nothing. So only the root that goes to infinity when epsilon goes to infinity is interesting here. What happens then? Then we have epsilon m squared is 4 divided by epsilon, so that would be go to infinity, and 2m, that would be -4 epsilon. Yeah, same order. So these two balance and go to infinity, while the third term is unity. So then these two first terms totally balance, meaning that this would be an approximate solution to this equation. We can of course get better estimates. This is the kind of crudest estimates we have. For instance, in the first one, we set, in this, we include the whole equation. And set m equals to the first root, approximate root, plus higher order corrections, and just insert that into the equation, and we can find m1, and if you want higher order, m2, and so forth. For the second root, if you want to have, so this would be by regular perturbation. The second root, okay, so how about writing n equal to -2 epsilons times m? So then we expect m tilde, so then we expect m tilde to be 1 plus something like that. Insert this into the equation and find m1, and we get better approximation for this other root. So it's kind of thinking basic reason. Okay, so we'll go further now and we'll study singular perturbation. The singular perturbation is characterized by that if I have some type of equation, either algebraic or differential equation or something, if we put this small number epsilon to 0, then the equation changes qualitatively. Here we go from a second degree equation to a first degree equation. So that's what kind of characterizes this other type of perturbation, that putting the small parameter to 0 changes kind of the situation. We also have this for differential equation. So let's have a heavy singular perturbation applied to differential equations. We'll start off with an example that's related to the previous example. Look at this problem. And then we have boundary values. So we're interested in so now instead we have a differential equation which we know how to solve actually, and we will kind of solve it too, just to illustrate the ideas. But here again we see if we put epsilon to 0, we get the first order equation. And for a first order equation we can only have one boundary value specified. Here we specify two boundary values, and that wouldn't work except when for some specific say value of I, this one or that one. So let's see what happens if we put epsilon to 0. We get this, and that's relatively simple to solve. So we see that the solution to the approximate equation by putting the first term equal to 0 gives us something like that, or gives us this. So we can possibly say, for instance, y of 0 equals 0 implies that this y is identically equal to 0. The only way to do this is to choose the constant k equal to 0. So, or if we use the other boundary condition, I guess we get something at least interesting here. We get that, I guess. See, for x equals 1, we have 1. But at x equals 0, it certainly is not 0. So this is a typical example where this small epsilon kind of matters in a sense, because we really want an approximation to the solution that honors both boundary value problems. The point is that, of course, this function here, or the solution to this, is very well described by this function on most of the interval. That's the clue here. I mean, this second degree equation is well approximated by this, as long as m is a finite number when epsilon goes to 0. But for the other root, it's different. So here, the idea is that this naive solution by putting epsilon to 0 is an approximation that actually is very good for almost all x between 0 and 1, except very close to 0. Then this solution kind of breaks down. So let's cheat a little and look at an approximation we get for free, because the characteristic equation for our differential equation so that's the same second degree equation as we just considered. So we have R1 is minus a half and R2 minus 2 divided by epsilon. So the two roots of the characteristic equation then gives us the solution, and since these roots are approximate, we have power of R1 times x plus c, or b times e to the power of R2 times x. So we see we get this additional term here, which includes epsilon. And since epsilon is positive, we see that when x is greater than epsilon or something, then this stuff is less than e to the power of minus 2. So when x is a bit larger than epsilon, then this term kind of disappears, and only this term is in action, which was our solution. So let's find the values of the constants first as well. So y of 0 equal to 0 means that we get a like that, because I see when I put x to 0, we get 0. And note that when we put x equals 1 here and assume that epsilon is really small, then this term is fantastically small. Say epsilon is 1,000, then it's e to the power of minus 2,000. Not much to draw about. So really we just choose this a to be e to the power of 1/2. So we have that so this would be a very correct solution for small epsilon, because we disregarded this term when we put x equal to 1. But we cannot disregard it here, of course. No matter how small epsilon is, when x becomes even smaller than epsilon, say epsilon equals 1/10 of epsilon, then this is closer and closer to 1, this term, when x goes to 0, however small epsilon is. And we see that this term here saves the boundary condition at x equals 0, that the function also is 0. We see that we get correct boundary condition. So this little term here is important on a very small part of the solution domain, assuming epsilon is small. And this small part here, let's try to kind of illustrate or draw the solution. So if we have one here, so the solution passes through this. And if we have, say, epsilon here, then when x is a bit larger than epsilon, then this term totally dominates. So we get, let's kind of draw this. So we get this solution. So this is that one. But when we pass epsilon, it kind of dives down to 0 due to this term. So in this small interval, typically the second derivative is large, meaning that this term will count. Other places on the solution, this term is small. So this small interval here, which shrinks when epsilon goes to 0, but no matter how small epsilon is important when we get below epsilon and we match the boundary condition. So this is called a boundary layer. And for this example, the boundary layer is estimated to be epsilon. It only needs to be a function of epsilon that where this function goes to 0 when epsilon goes to 0. So we could have a boundary layer that was like the square root of epsilon. That would be possible. Or epsilon squared. Whatever. Depends on the equation and the situation. The boundary layer of such problems are usually situated either close to 0 or close to the other endpoint of the interval, close to 1 here. That also depends on the problem at hand. And often it's not so easy to know beforehand how to determine where the boundary layer is. But if we choose the wrong end, we'll soon get into trouble when we do our singular perturbation analysis. So far we haven't done much of this analysis. We have actually solved the equation and disregarded the small term. So, and also we see that this naive solution, very nice, gives the whole solution on almost all of the interval. So these are kind of the ingredients we have back in our head when we look at this singular perturbation analysis. Okay, so let's forget everything about this solution and go back to the original problem with the same boundary values and try to analyze it the way we're supposed to analyze this type of equations. Of course, we can solve this by hand, so why bother doing all this shit with this equation? But the shit I'm going to show you can be applied on more or less any type of problem. Also problems we can't solve by hand. And after we have gone through this example, we'll apply it to this biochemical reaction, or the kinetics of a biochemical reaction, where we have one substance being converted to another substance with the help of an enzyme. And we'll look at the reaction rates of the different reactions and set up a system of differential equations which are nonlinear, which we can't solve by hand, but where we can do singular perturbation analysis and obtain approximate answers. Of course, in these days, people like to use the computer I'll also try to show you some graphs next time. But thinking about it, when you do simulations, all you get are examples of solutions, numerical examples. And you can see, okay, and I increase this parameter, it seems that it grows over here. But when we do this analysis I'm going to show you now, we usually get expressions that are approximate, just like this liver stuff, no, sorry, kidney stuff, which are actual formulas. And that's a lot better, of course, than all these graphs that the numerical experiments would give you. Yes, so let's do some singular perturbation. The idea is that we first look at this so-called naive solution, or it's called the outer solution, because here we have the boundary layer, and outside the boundary layer, this solution describes the full solution very well. And so this is called the outer solution. That's the one we find first. So we have our equation. And putting first, find outer solution. And by setting epsilon equals 0. Okay, but then we got the first order equation. We have two boundary conditions. And then it's quite logical that since this solution, outer solution, approximate the real solution outside the boundary, we use the boundary condition outside the boundary layer. Since the solution let's give it a name. Call it O, not why not, but why O router. Let's general call this boundary layer. The width of the boundary layer doesn't necessarily have to be epsilon, so let's be general now first. And say it's somewhere let's be a bit more general, because we really don't know now that the thickness of this boundary layer is epsilon actually. So let's just call it something where we know that this boundary layer shrinks to 0 when epsilon shrinks. Okay, so we get this as I showed you. So this is the outer solution. But we can't meet the boundary conditions at x equals 0 with this one. So how do we go about finding, kind of, by analysis, by perturbation analysis, how do we find this other term, which is important in the boundary layer? Well, the philosophy is that we look at we kind of stretch this boundary layer out, because if we have a function that If you define this function, capital Y, I mean, we have this variable C equals this, then this capital Y of C equals Y so that means that if this C here goes from 0 to 1, then X goes from 0 to delta only. So we kind of stretched out the boundary layer to be unit length regardless of what epsilon is. And then we try to find the differential equation for this capital Y. And this will kind of move the small parameter to a different position in the equation, in a sense. And also tell us how to choose this delta. So from here then, we know that epsilon delta plus 2 y plus y equals 0. Then if we use this expression instead, and the chain rule, we get epsilon divided by delta squared. If I take the double derivative of x, plus 2 divided by delta so now we have the differential equation, and we can also assume actually that these terms are of order 1, since our solution so we have delta here, so this y function is something like something like that, I guess. Because when this traverses 1 unit, the height traverses approximately 1 unit, so the derivative should be approximately 1, y should be 1, and the second derivative shouldn't be too bad. So that means that, so that's because we have stretched out the domain regardless of how thin the boundary layer is. This C stays between 0, and 1 and covers the boundary layer. That means that these so that means that these coefficients then really give us essentially the size of each term. So now we have to again we have to find delta such that 2 of these terms balance and 1 is much smaller. Yeah? Yeah, 2 of them. Thanks. It's correct. But still, now we're talking kind of what order these are when epsilon goes to 0, how fast they go to infinity, are they order 1, do they go to 0, whatever. So, just by inspecting here, we can see that when if you choose delta to be epsilon, that the width is actually the same as epsilon, then this is 1 divided by epsilon, this is typically 1 divided by epsilon, and this is order unity. So when epsilon goes to 0, these two go to infinity at the same rate, and this one is diminishingly small. So choosing, we could choose delta equals to 10 times epsilon or whatever. It's the order that's important. Choosing gives approximate, gives, yeah. So I get this equation. So now we have moved the epsilon to the last term instead for this. And this equation has a name. It's called the inner equation. And of course, this is kind of relevant then in the boundary layer. So for this equation, we choose to use the first boundary condition at 0, the boundary condition that's situated in the boundary layer. So y of 0 equals 0. Set, that means that this of 0 must be 0. So that will be a boundary condition for capital Y. So putting, we now get to again find the 0 order approximation to this equation by setting epsilon equal to 0. We get this one. And so we have then y of this xi equals, what will it be? It will be, a constant will be, let's call it d plus e times. So that we do in our head. Has characteristic equation r squared plus 2r. So r is minus 2 or 0. Sorry. And then capital Y of 0 equals to 0 gives or E equals to minus D. So we have whatever I write here. And we see that that satisfies the boundary condition at xi equals 0. And we see that when we substitute for this, this term that we found from using the formula, because then we get minus 2 times x divided by epsilon here. When we go back to the solution in terms of x. But we still have this unknown constant, so how to kind of determine it? Because now we have two solutions. We have one that is valid by replacing this with x divided by epsilon. We have a solution that is very correct at the very start, but then this goes to 0 quite quickly, so it won't matter when x is larger than the boundary layer. So how do we determine E? What do? You want to match our two equations. Oh, sorry, functions. This one was so these are kind of the two expressions we have. So what we want to do is to match these two functions. And in a sense, this is maybe a bit fishy. We have the boundary layer here. And we have our function x there. 1. And then we have our kind of outer solution here. So we kind of want to match our two solutions at some point where they are equal. So let's take matching. Depending on how large epsilon is, let us match the two solutions at x equals some number as a function of we'll match them and then let epsilon go to 0. The nice thing is that we really don't need to know much about this theta of epsilon, but we want it to be just kind of outside the boundary layer, but still it will follow the boundary layer towards 0. So what we require of this function is one thing, namely that goes to 0. So it kind of follows the boundary when epsilon shrinks the boundary. But we don't want it to follow too quickly. We want also that it's a bit slow approaching that, because we want it kind of to be outside the boundary. So we want it to go slower to 0 than what the boundary layer does. So, for instance, if the boundary layer is epsilon, then say epsilon to the power of 2, sorry, epsilon to the power of say this suddenly okay, so it has to follow there, and well, this is correct. So if this is epsilon, we could say this is the square root of epsilon, so that's correct. So I get 1 divided by the square root, which goes to infinity, and the square root of epsilon goes also to, so x, I'll just take the brakes right now. Delta v epsilon, delta v epsilon half. Then we see that these things would be. So that would be one choice then for, but we don't need to choose it, that's the beauty of it. And I'll come back to that after the break. And I'll give a small recap of what we did.